So last topic regarding Poisson process is merging and thinning. They are very important concept. Very important concept and the properties of Poisson processes. Okay. If we consider two independent Poisson processes, let's say N1 and N2. They are Poisson processes with rate lambda 1, lambda 2, respectively. They are independent. Then we can consider new process n of t, which is the same as n1 of t plus n2 of t. Let's think about the market. We can count number of male customers. Let's say this one is N1, number of male customers in front of the market, E-mart, department, Lotte department, okay, in front of department. You can count number of male customers, 1, 2, 3, 4, as time goes on. And how about number of female customers? We need to calculate, we need to count differently. Right? Independently. So we assume that this arrival process of female customer is independent of arrival process of male customers. Okay? We assume. And then your boss is try to see arrival process for all the customers. Let's say there exists two different kind of human, male and female, let's say we assume. Then the number of customer can be calculated by number of male customer plus number of female customers up to time t. Okay. So if we assume that number of male customers arrive to the department by time t follows Poisson process with lambda 1, rate lambda 1. Okay, and then number of female customers who arrive to the department by time t follows Poisson process with rate lambda 2. Then, how can you examine number of customers? Probability regarding number of customers, general customers, whether this one is customers are female or not. Then, in that case, n of 1 plus n of 2, n sub 1 plus n of sub 2, n of t can be defined as n of 1 t plus n sub 2 t. This one is Poisson process. Poisson process with lambda 1. Poisson process with lambda 2. Then total might be Poisson process with rate lambda 1 plus lambda 2. We call this merging. So if we see this, as time goes on, we can check every time a male customer arrives to the system, then we can mark this blank circle. Okay, this time, and then every time female customer arrives to the department, then we can mark. Okay, black circle. This time, second female customer arrives. Third female customer arrives, and so on. If we sum these two processes, then we can check any circle, whether blank or black. So, first customer, second customer, third customer, fourth customer, and so on. Okay, this one represents this process regarding any customer. So this one is also Poisson process. Rate lambda 1 plus lambda 2. We can consider the other way around. Okay, customer arrives. Let's say a multiplex movie theater. This multiplex movie theater run 2 different movies like Star Wars and Titanic. Okay, we don't know who want Star Wars or Titanic. We don't know. We just count the number of customers, but we know that with probability P, after entering to the theater, then with probability P, this customer want to see Titanic. With probability 1 minus P, customer want to see Star Wars. Okay. Then in front of the room, okay, I mean check your ticket or something like that. Okay, in front of the screen room. Okay, you can check number of customers who want to see Titanic. Okay, this is another arrival process, right? And in front of the other room, okay, for Star Wars, you can count number of customers who want to see. So split the customer, okay? Split the customer with probability P and 1 minus P. P and 1 minus P. So suppose that number n represent Poisson process with rate lambda. After arriving to the system, they are split it with probability P and 1 minus P. Okay, first place with P and second place with probability 1 minus P. Then let's say for the first place, we can check the count of we can count the number of customers. Okay, this one, let's say this one is n sub 1, and in front of the second place, you can check the number of customers. Okay, let's say this process is n sub 2. Then they can be considered as two independent Poisson process with rate lambda p and lambda times 1 minus p. Even though we consider more than 2 places, 3, 4, 5, 6, 7, and so on, it works with pi. So enter to the system like theater, and then split it room 1 to room 10 with probability P1 to P10 and so on. Okay, in front of the room, you can check the number of customers, but this one is actually Poisson process with rate lambda P1. In front of 10th room, T is Poisson process with lambda P10. Okay? And they are independent. We call this thinning process. Very, very important property of Poisson process. So we can use many different ways to calculate the probability expectation regarding the processes. Okay, can be n of t or n sub 1 of t and so on. Okay. Example 8. I think as long as you can understand thinning and merging, it is not that easy to calculate it, to find the answer, but number 3 is quite complicated. Okay, quite complicated. So let's think about this. Suppose n of 1, n of 2, they are independent Poisson process with rate lambda 1 and lambda 2 respectively. And n of t, merged process such as n of t equals 1n sub 1 of t plus 1 and sub 2 t plus t.